Now I'm just briefly going to go over the physics of this so that we can get a definition of entropy. So the first law of thermodynamics, energy cannot be created nor destroyed, which is similar to the chemistry law, matter cannot be created or destroyed that we use to balance our equations. But Einstein sort of stuffed that up and said energy can turn into matter and matter can turn into energy, but that's physics. So let's not get too carried away. We're not doing nuclear reactions. Okay. Second law of thermodynamics is what we're doing. Entropy always increases. That's conceptually. And now we're sort of doing calculations. So the third law of thermodynamics is entropy is zero when it's a crystal at 0 Kelvin. So that's where the numbers come from. So we're really moving on to the third law. Again, the physics guys do all the heavy lifting. That's the heat capacity, not specific heat. So how much heat can it contain and how many different combinations? And this is cumulative. So even though it's going down, it's not actually going down. It's going up and up and up because it's cumulative. And the jumps here are because they're not just calculating the heat capacity, they're also adding in the extra changes of state, as heat of fusion is melting and heat of vaporization is boiling or evaporating. And so there are these jumps where it would normally just go down. We're getting extra values added. And so that's just a brief overview. It's way beyond the limits. I think it's perhaps beyond the limits of a physics degree, but when I talked to the physics teacher, he was not very keen on trying to explain how they come to this. It's very complicated, but they do it, and this is the value that you get. Okay, so they're always positive because these things are starting off as a crystal, theoretically. Sometimes I have to do a bit of Hess law stuff for that. They have to do some, I think it's quantum mechanics or something to try and work out how to get that into a crystal at 0 Kelvin. And then they always go up from there, obviously, because they're increasing in temperature and changing state. And so that's where it comes from. So you don't have to worry about too much as long as you've got a general idea of how they get to it, because once again, you got to know what the formula is. So they're all positive values going from 0 to something else, all right, to the state that they're in, which is way above 0, and most likely a change of state as well. And so this must be reversed, and this can stay as is. So it's products minus reactants. So you do need to know it kind of to be able to work out its products minus reactants. Okay, and then you can just do the calculations as we've been doing all the entropy calculations. You just add up all the entropies. And so practice calculation. So what is the enthalpy change? So we already know it's products minus reactants. All right. You look it up. These ones are in the data booklet. Okay, and so we just add them up correctly. It's for this reaction. And so we're halving this in this case. We're just doing what the question says. This is an enthalpy of formation, by the way, but you just asked for the entropy of formation. It is, but you asked for the entropy change. That's all. So just doing what it says. All right. So products minus reactants. This one is products. These two are reactants, and this one here was halved. Okay, so substitute, just check that I haven't swapped those around incorrectly. That should be around the other way, but that's correct. That's the right one. That's the oxygen, that's the hydrogen. And that's the number, and you're done. Okay, so yeah, it's just plug and play, basically. The physicists have done all the hard work.